We're going to continue on with Unit 6, and in this video we're going to focus on learning Target 7E, which is all about solving exponential and logarithmic equations. So by the end of this lesson, we will be able to solve exponential equations that have the same base, as well as solve exponential equations that have different bases. We will also be solving logarithmic equations with one log, as well as solving logarithmic equations with multiple logs. So let's start off with the exponential equations. Our first case that we're going to be looking at is when we have the same base. And these are going to build off of examples that we've talked about in prior sections. So in our first example here, we have 8 to the 2x minus 1 equals 16. And our goal is to be able to solve for x. And in this case, we can get the same base on both sides since both 8 and 16 have a common base of 2. So we're going to start this off by rewriting both 8 and 16 so that they can be 2 to a power. Now for 8, we could rewrite that as 2 to the third, and we'll still have the 2x minus 1. And we could then rewrite the 16 to be 2 to the fourth. From here, I just want to multiply my two exponents, so we'll have 2 to the third times 2x minus 1. And it's important here to make sure that we do have the parentheses around the 2x minus 1, since the 3 would be distributed to both pieces. And then we still have the 2 to the fourth. From here, since we have the same base, we can set the exponents equal. So because I have 2 to something equals 2 to something else, that means that those two exponents then of 3 times 2x minus 1 on the left side has to equal the exponent on the right side, which is 4. Now from here, this is an equation that we could solve. We could distribute the 3 and get 6x minus 3 equals 4. And from here we can combine like terms to isolate the x. Why don't you guys pause the video and finish solving this one out. So to check this, we'll add 3 to both sides, and we end up getting 6x equals 7, and then divide through to get x by itself, and we get a final answer of 7 over 6. Let's look at another example where we can get the same base. Here we have 81 to the 5x plus 2 equals 1 over 27. Both 81 and 27 can be rewritten as 3 to some power. So why don't you guys pause the video here and rewrite the left side so that we have 81 rewritten as 3 to a power, as well as rewrite the right side so that we get the 1 over 27 rewritten as 3 to some power. So on the left side, we can rewrite 81 as 3 to the fourth, and then we still, of course, have that 5x plus 2. And on the right side, I'm going to do this in 2 steps, but we can rewrite the 27 as 3 cubed, but I still have the 1 over 3 cubed. From here, I'm going to flip that exponent so that I end up getting the 3 in the numerator, and I'll end up with 3 to the negative third. Since we moved that base from the denominator to the numerator, the exponent is multiplied by a negative 1. And then on the left side, I just have the 4 times the 5x plus 2. Now from here, we have the same base on both sides, so we can go ahead and set the exponents equal and solve for x. Why don't you guys pause the video and complete this on your own. Okay, let's check this. So we're going to have the 4 times 5x plus 2 equaling to the negative 3. Since my bases are equal, my exponents are equal as well. I can distribute the 4 to get 20x plus 8 equals our negative 3. Subtract the 8 over to get 20x equals negative 11, and then divide through by the 20 to get x by itself, and we'll end up with a final answer of negative 11 over 20. In our third example here, this will also be a same base type of case that we have. We have 32 raised to the x plus 4 equals 8 raised to the 2x. I want you guys to try this one on your own, and we'll check this at the start of our next class together. Let's look at what happens if we have different bases. So in example 4 here, we have 9 to the 4x equals 80. Now this is just slightly off. If this was an 81 instead of an 80, we could rewrite these with the same base. But in this case, 9 and 80 don't share a common base factor that we could rewrite this as. So we need to have some other way to solve this. Well, we learned that logs and exponentials are going to undo each other because they are inverses. So what we can do is we can apply a log to both sides of this equation. So I'm going to take the log of the left side, So I have log, I'm going to use base 10, so I don't need to go ahead and write the base. I assume that that's base 10. We get log of 9 to the 4x equals log of 80. And as it looks right now, it almost looks like we made this more complicated. But the reason this is helpful to apply a log to both sides is now we can use the power rule for logs, or power property, and bring down that exponent, and the 4x can move down in front of the log, and we get 4x times the log of 9 equals the log of 80. And in this case, it's okay to apply the log to both sides of our exponential equation because we're doing the same thing to the left side as well as to the right side, and they're both the same log base 10. Now from here, our job is to isolate the x. And now that the x is outside of the exponent, by using that power properties of logs, we can go ahead and divide through by the 4 times log of 9 to get the x by itself. But then I have to divide through on the right side as well. So we get 4 times log of 9 here. On the right side, the 4's cancel, or reduce down, and the log of 9 reduces down as well, to just leave us with x equaling log of 80 over 4 times log of 9. Now from here, there's not much more that we can do to simplify. The one thing I can do is apply the power property again, just to condense this down as much as possible. And we'll end up with x equals log of 80 over log of 9 to the 4th by applying that power property one last time. Now we are unable to divide these two log expressions because the quotient property requires that the logs are subtracted in order to divide their inputs. But in this case, if I have log of a number over log of another number, I cannot simplify that any further. And this right here is actually going to be our final answer. I know it looks really funky to have logs in our answer. Up above we were getting nice rational numbers as our values, but log of a number is actually a numerical value. We could type this into a calculator and get a decimal approximation, but if we want the exact answer, we actually want to leave it in this form and not use a calculator, because a calculator is approximating these irrational numbers. Let's look at example 5. So we have 12 to the 2x minus 1 equals 5. Again, 12 and 5 do not have some common base that we could rewrite both of those numbers as. So we're going to go ahead and apply the log to both of sides to get log base 10 of 12 to the 2x minus 1 equals log base 10 of 5. The advantage here of applying the log is that we can now use the power property and bring down that 2x minus 1, and will be multiplied to this log base 10 of 12. Now it's important that we have those parentheses around the 2x minus 1 because that whole quantity is being multiplied to the log log base 10 of 12. Now from here we want to isolate and get the x by itself, so I'm going to distribute so we can get rid of the parentheses to get the 2x times log of 12 minus 1 times log of 12 equals our log of 5. Before I divide through to get x by itself, I need to go ahead and add the log base 10 of 12 to the other side. So we still have this 2x times log of 12, but now that will equal log of 5 plus log of 12. From here we are going to go ahead and divide through, but one thing I want to point out is we can actually condense this down even more. When I have two logs with the same base that are being added together, we can use the product property and multiply their input. So we'll get log base 10 of 5 times the 12, which will simplify to be 60. Now to get the x by itself, we're going to go ahead and divide through by 2 times the log base 10 of 12 to get x equals the log of 60 from the 5 times the 12 over 2 times log of 12. Now our last step from here, just to condense this down as much as possible, would be to move that coefficient up into the exponent, and we get a final answer of log base 10 of 60 over log base 10 of 12 squared, or if we want to simplify 12 squared as 144, that would work as well. and that will be our final answer. So when we're able to get the same base on both sides, there's no need to take the log because we can just get the same base and set the exponents equal to each other, and that's going to allow us to get a nice rational number as our answer. And if we have different bases, we have to apply the log to both sides. And technically it doesn't matter which base we use. I just use base 10 out of convenience for not having to write a base that way, but as long as we use the same base on both sides, this will work out. And the reason we wanted to apply that log was to be able to use that power property, which moves that exponent inside of the log to be a coefficient out front. Same thing over here with example 5 by moving the 2x minus 1. Then from there it does take some algebra to simplify and get any combined like terms that we could using any properties of logs, and then we just want to isolate our variable. Now there's one more example of this type. It's problem 6, and I want you guys to try that one on your own as well, and we'll check that one at the start of class next time. Let's look at our log equations. So the first couple examples we're going to see just has one log. So for each one of these 4 examples, we just have a single log, and we're going to solve for that variable. So looking at example 7, we have log base 81 of x plus 2 equals 1/2. Well, our goal is to get the x by itself, and right now it's the input to this log function. Well, we can't get rid of this x and take it outside of the log without getting rid of the log completely. And one way to get rid of a log expression or a log equation is to rewrite it in exponential form. So we're going to convert this from log form to exponential form. So our base in our log is 81, so that's going to be the base of our exponent. Our output to our log becomes our input or our exponent, and that will be equal to our input on our log. So what we're using here is that conversion from log form to exponential form. What this allowed us to do is get the x, which was the input to the log, to be the output to the exponential, so we can isolate and get x by itself. Now if we can simplify anything else, we'll want to do that as well. Now the 1/2 power is the same thing as the square root, so we really have the square root of 81 equals x plus 2. Since 81 is a perfect square, we can go ahead and take the square root and get 9 equals x plus 2. And then to get x by itself, we can subtract the 2, and x is going to be equal to 7. Let's look at our next example. Here we have log of 2x minus 4 equals 2. Again, our variable is inside the log, and the only way to get it outside the log is to convert to exponential form. What would our base be in this case? So in this case, our base is 10, since we have that log without anything written in our base. So why don't you guys pause the video and convert this from log form that it's in right now to exponential form. So to convert to exponential form, we'll need our base to our exponent of 2 will be equal to 2x minus 4. Now from here, this makes it a lot easier to solve for that x since it's no longer inside of a log function. We can simplify the 10 squared. 10 times 10 would give us 100 equals the 2x minus 4. Add the 4 to the other side to get 104 equals the 2x. Then when we divide through by 2, we can actually simplify that to get x equals 52. And that will be our final answer. Okay, let's look at example 9. We have log base 3 of x minus 1 equals negative 1. What do you guys think our first step will be to solve this log equation? So our first step here will be to convert to exponential form. Why don't you guys pause the video and convert this to exponential form, and then we'll check that together. So in exponential form, we'll have a base of 3 to the negative first equals x minus 1. Now, to simplify the 3 to the negative first, we'll want to rewrite that to be 1 over 3 to the positive 1 by flipping that to flipping it from the numerator to the denominator. From here, to get x by itself, we want to add 1, so we get 1/3 plus 1 equals x. In order to combine those two, I need a common denominator, so we can go ahead and rewrite the 1 as 3 over 3. and then we can get our value by adding our two numerators to get x equaling 4/3, since we had that common denominator. Let's look at example 10. Here we have log base 2 of x plus 5 equals 8. So in number 10, we still just have one log, but we have multiple extra terms here. In 7, 8, and 9, each one of these had the log isolated on the one side together. Over here, we have a log plus another value. Before we can convert to exponential form, we actually need to isolate the log base 2 of x, and to do that, we would subtract the 5 over to get log base 2 of x equals 3. From here, we're able to convert to exponential form and then solve for x. Why don't you guys finish up example 10 on your own, and then we'll check it together. So to continue on with problem 10, we want to convert to exponential form, which would be 2 to the third equals our old input of x, and then simplifying 2 to the third, we find out that x is equal to 8. And that will be our final answer. Let's look at a couple more of these examples with one log. So in example 11 here, we have log base square root of 13 of 13 equals x. And you might be thinking, well, the x is already isolated. I'm good. I was able to get the x by itself. They gave it to us that way. Well, in this case, we can actually simplify this further, and we want to figure out what rational number this would be equal to. So we're going to do the same process we did up above by converting to exponential form, and then it's actually going to turn into a same base exponential equation for us to solve. So why don't you guys pause the video here and rewrite this in exponential form. So to check our exponential form, we'd have a base, which is the square root of 13, a little funky, to the x power equals 13. Now from here, we want to use what we know about radicals, and we can rewrite the square root of 13 to be 13 to the 1/2 power, all raised to the x still, equals 13. And now that I have the same base on both sides, I can set the exponents equal. On the left side here, our exponent is 1/2 times x, and on the right side, we have an exponent of 1. Since we have the same base of 13 on both sides, we can go ahead and set those equal, and we get 1 over 2 times x equals 1, which, to get x by itself, multiply through by 2, and we get x equals 2. So even though we had x already isolated to start off with in this problem, we did want to simplify that as much as possible, and so it is convenient in this case since we are able to get a same base on both sides. If I tried this and I could not get a same base on both sides, then that would actually be our most simplified answer. Examples 12 and 13 are two more additional problems dealing with a single log that I want you guys to try, and we will check at the start of our next class as well. Okay, let's look at the case when we have multiple logs. So multiple logs, to solve these, is going to require that we first get it down to a single log expression and then apply the same concepts that we used up above. So on example 14 here, we have log base 6 of x minus 5 plus log base 6 of x equals 1. And our first step is to condense this down into one log expression. Any ideas on how we could condense this down using properties of logs? Well, we can use the product property. Since we're adding two logs with the same base, using the product property tells us that we can rewrite that and condense it down as a single log where we multiply the two inputs. So we are going to get log base 6 of x minus 5 times x, and that will all still be equal to 1. From here, let me go ahead and distribute everything inside to get log base 6 of x squared minus 5x equals 1. Now from here, this looks similar to what we had before. The difference though is that we do have an x squared and an x, but we'll worry about solving that later on. What I know I need to do first is get this from log form to exponential form. Why don't you guys pause the video here and convert from log to exponential form. So exponential form, we would have a base 6 raised to the first power equals that x squared minus 5x. Now 6 to the first power is just going to leave us with 6. We still have that x squared minus 5x. Now this is a quadratic equation. What would be the easiest, nicest way to solve a quadratic equation? Well, we have lots of options to solve quadratic equations that we learned about last semester. And one of the nicest ways would be if we could factor it and use the zero product property. Alternative ways would be completing the square. We could use the quadratic formula as well. Well, let's see if we can go ahead and factor this. In order to do so, I need to get the 6 to the other side. So I'm going to subtract 6, and we get x squared minus 5x minus the 6. What do you guys think? Can we factor that quadratic equation? So yes, we can. We're looking for two numbers that multiply to be -6 and add up to be -5. -6 and +1 will work because -6 times 1 will give me -6 and -6 plus 1 will give us -5. So from here, we're going to go ahead and factor that quadratic into x minus 6 times x plus 1. Using the zero product property, we can set each one of these factors equal to 0. So we get 0 equals the x minus 6, and we also get 0 equals the x plus 1. And from here, we can solve each one of these, and we get that x is equal to 6, and we also get that x would be equal to -1. Now, because we created a quadratic equation, we could actually produce answers that are not real solutions to this equation that we have. And the reason this happens is because the domain of a log function is strictly positive numbers. When we looked at just y equals log base b of x, and we looked at that graph, let's assume that our base is bigger than 1, but we had a graph that slowly grew over time. And what we also had was we had a vertical asymptote here at x equals 0. Now, because of this vertical asymptote, our domain was strictly greater than 0. Depending on what transformations happened, of course the vertical asymptote in the domain shifted, but what I know for sure is that whatever my input is in a log has to produce a positive number. So what that means is we need to check both of these answers into the original problem. And we're going to check them by subbing them into the inputs. So we need to sub 6 and -1 into x minus 5, as well as into the single x. If we sub them in and they both cases produce a positive number, then that will work as a final answer. If we sub either of these in or both of these in, and we end up getting a negative input to our log, then that's going to produce an issue. So let's check this. Let's start with the x equals 6. If we sub that in, we'll get log base 6 of 6 minus 5, and 6 minus 5 is equal to 1, so that would work. If we just sub it into the x, then we get log base 6 of 6, and that's also a positive number, so that one works as well. So what that tells me is that x equals 6 is in the domain of my equation that I'm starting with. Now let's check the -1. If we sub it into the x minus 5, we're getting -1 minus 5. This value right here would produce a negative input. I cannot have a negative input to a log and get a real number out. This is not producing a value that's in the domain of this function. Because of that, x equals -1 is what we call an extraneous solution because we have a domain issue here. Now, if you scroll back and you look at all the prior examples, we didn't talk about this because it wasn't going to be an issue. Because we only had one log in each one of these, we knew that our answer was going to produce a valid solution. And if we were to go back and check here, I could sub in 7 into example 7, and I'd get log base 81 of 7 plus 2. 7 plus 2 is a positive number, so we're good. We could do the same thing with the 52. 2 times 52 minus 4 is definitely a positive number, so this one works as well. And we could check examples 9 and 10 as well. But when we have two logs, because we had to use the product property for logs and multiply their inputs together, that produced that x squared, which is potentially going to give us an extraneous solution. Now, not all of them will produce an extraneous solution, but there is a very high probability that we will get one. Let's look at one last example with two logs. So here we have log base 2 of x plus 1 plus log base 2 of x minus 5 equals 4. First thing we have to do is condense this down into one log expression. Why don't you guys pause the video here and use whatever properties of logs we need to condense this down. So using the product property, we could rewrite this as log base 2 of x plus 1 times x minus 5 still equals 4. I'm going to go ahead and distribute all of that out inside to get log base 2 of x squared minus 5x plus x minus 5. Combining some like terms, we get log base 2 of x squared minus 4x minus a 5 equals 4. Now that we've condensed this down into a single log expression, we can go ahead and convert to exponential form. Why don't you guys pause the video here and convert this to exponential form? So in exponential form, we'd have a base of 2. Our exponent would be 4, and that would be equal to x squared minus 4x minus 5. Get a little bit more space. From here, we want to go ahead and see if we could factor this again. So I'm going to simplify the 2 to the 4th. 2 to the 4th is equal to 16. And then I'm going to go ahead and subtract the 16 over just so that we get all of our quadratic equation here in standard form. So we'll get 0 equals x squared minus 4x minus 21. Now from here, it would be really nice if we could factor this quadratic equation. Are we able to factor x squared minus 4x minus 21? So in this case we can. We're looking for two numbers that multiply to be negative 21 and add up to be negative 4. Negative 7 and positive 3 would work. So we end up getting 0 equals x minus 7 times x plus 3. From here, now that it's in factored form, we can use the zero product property and split this apart and set each factor to 0. So we get x minus 7 equals 0 and x plus 3 equals 0. Solving each one of these for x, we end up with two potential solutions, x equals 7 as well as x equals negative 3. Now since we had to combine logs and produced an x squared, we want to make sure that both of these are valid solutions and that none of them affect or give us a domain issue. So why don't you guys pause the video here and start by checking x equals 7. Sub that into the original and see if we still get all of our inputs for our logs to be positive numbers. So to check this, we want to make sure that log base 2, if I sub in 7 here, we'd get 7 plus 1. So that would give us a positive number. That works out. We also want to sub it into the x minus 5. So we get 7 minus 5. That still is a positive number, so this works out as well. So x equals 7 is a valid solution. Now, just because x equals 7 worked does not mean that negative 3 won't work. We have to individually check this one as well. So why don't you guys pause the video here and check the x equals negative 3 and see if that works out as a solution. So subbing in the negative 3, let's start with the first log of log base 2 of x plus 1. In this case, negative 3 plus 1 is going to give us a negative 2, which is less than 0, and so this is giving us a domain issue. And we're getting that domain issue because we cannot have the input to a log expression be a negative number. So x equals negative 3 is an extraneous solution, and our only valid solution here is x equals 7. So in this video, we talked about quite a few things, how to solve exponential equations as well as log equations. For exponential equations, we had the same base type, and then for log equations, we had the 1 log versus the 2 log. Now there were a couple problems that I left for you guys to try. Please make sure you guys try those before our next class, and we're going to check those as a warm-up at the start of our next class.